Hello, and welcome to our video on the convolution. We now know that the Fourier transform is linear in the following sense. If you have functions f and g in L1, and scalars alpha and beta in the complex plane, and if you take a real number k, then the Fourier transform on alpha f plus beta g evaluated at k is alpha times the Fourier transform on f at k plus beta times the Fourier transform on g at k. But functions have another operation. We can of course add functions together, we can multiply them by constants, but we can also multiply two functions together. And of course we take the product of f and g at x to be f of x times g of x. So if I have functions f and g in L1, what, if anything, can we say about the Fourier transform on the product fg at k? In other words, what is fg hat of k? And the natural guess might be to say that fg hat of k is f hat of k times g hat of k. We might guess that the Fourier transform of the product is the product of the Fourier transforms. After all, the Fourier transform of a sum is the sum of the Fourier transforms by linearity. And this guess for the product is wrong, which is why I've typed it out in red font here. First, we have a more subtle problem. Say I have functions f and g in L1 of R. That doesn't guarantee that their product, f times g, is back in L1 of R. You can cook up some nasty examples of this. And so even though f and g separately may be in L1, their product may not be in L1, and so the Fourier transform of the product need not be defined. So that's something we should work out first. When can I guarantee that if f and g are in L1 plus something else, then fg hat is defined? Turns out that if you take f and g in L2 of R, then yes, their product fg is in L1 and their Fourier transform is defined. So let's see why this is the case. First, we're going to take numbers a and b in the reals, and we're going to estimate the following thing. 0 is less than or equal to the quantity a minus b squared. Well, that we've known for years because squares of real numbers are always non-negative. Now what's a minus b squared? That's a squared minus 2ab plus b squared. Just expand out the square. So what does that tell us? I'm going to put the 2ab on the other side and divide by 2. This inequality rearranges to give me ab is less than or equal to a squared over 2 plus b squared over 2. So if I have functions f and g in L2 of R, what does this inequality tell me? Well, the modulus of the product, f of x times g of x, is less than or equal to modulus of f of x squared over 2 plus modulus of g of x squared over 2. All I did was take a equal to modulus of f of x and b equal to modulus of g of x. Now let's use the comparison test. If I'm assuming that f and g are in L2, then modulus of f squared and modulus of g squared are improperly integrable on R. And so I've bounded modulus of f times g by modulus of f squared plus modulus of g squared over 2. So the comparison test tells me that the modulus of f times g is also improperly integrable on R, and that means that fg is in L1. Now it turns out on the previous slide that the bad idea, the non-equality, the fallacious identity, fg hat of k equals f hat of k times g hat of k, that's bad, but it gives us a way of going forward for computing the Fourier transform of the product. What can we say about the product on the right-hand side here? What can we say about f hat of k times g hat of k? It may not be obvious, but that's going to give us the right answer for what is fg hat of k. So let's start with functions f and g that are in both L1 and L2. So what does this give us? We have three Fourier transforms defined now. F hat and g hat are defined because f and g are in L1, and fg hat is defined because f and g are in L2, so the product f times g is in L1. And we're going to figure out what can we say about the product f hat of k times g hat of k. And eventually this is going to turn into something about the Fourier transform of the product fg. So let's start out just calculating f hat of k times g hat of k. This is, I'll combine my factors of 1 over root 2 pi to give me a 1 over 2 pi, times the integral of f of x times e to the minus ikx, times the integral of g of y times e to the minus iky. So all I've done here is write out the Fourier transforms in their integral form and collect the root 2 pi constants. Now you'll notice that in the first integral I'm using the dummy variable of integration x, and in the second integral I'm using the dummy variable of integration y. This is often useful when you're multiplying two integrals together, have two different variables of integration. Sort of like when you're taking a double sum, having two different letters of summation is helpful. So let's put these integrals together. So this is 1 over 2 pi times the double improper integral, minus infinity to infinity, minus infinity to infinity, f of x times g of y, and then in the exponential I've combined things. This is e to the minus ik, x plus y, and it's a double integral now, dx dy. So I'm going to fix my variable y. I'm going to fool around a little with the inner integral. So with y fixed, I have the integral from minus infinity to infinity f of x times g of y times e to the minus ik x plus y dx. I'll pull out the g of y, and this gives me integral minus infinity to infinity f of x e to the minus ikx plus y. And you'll notice that I'm keeping the y part of the exponential inside the integral. I'm not pulling that out too. Because now in that exponential I'm going to substitute u equals x plus y. So I'll get du equals dx. And then I can rewrite x equals u minus y. And this tells me that the integral from minus infinity to infinity f of x e to the minus ik x plus y dx is really the integral from minus infinity to infinity f of u minus y e to the minus iku du. So if I go back, I see that I've written f hat of k times g hat of k as 1 over 2 pi, integral minus infinity to infinity, integral minus infinity to infinity, f of u minus y times g of y times e to the minus iku du dy. This may not appear at all helpful, but we're going to see that it really, in fact, is. Suppose we can interchange the order of integration here. In other words, that we can do a Fubini's theorem for double improper integrals, which is a little delicate once you start putting the improper integrals in there instead of just regular bounded integrals, but trust me, it works. So we want to go from integral minus infinity to infinity, integral minus infinity to infinity, f of u minus y, g of y, e to the minus iku du dy, to integral minus infinity to infinity, integral minus infinity to infinity, f of u minus y, g of y, e to the minus iku, so entirely the same thing, except now it's dy du. What does that mean? I can pull out this u-dependent exponential from this inner y integral. So I have the integral from minus infinity to infinity, integral minus infinity to infinity, f of u minus y, g of y dy, and then e to the minus iku du. And if I stare at this a little bit, the inner integral, the dummy variable is y, and u is an independent variable. So that inner integral is really a function of u. So in the big parentheses, I have a function of u, then I have times e to the minus iku, and I'm integrating with respect to u. This looks an awful lot like a Fourier transform of the function that's inside the big parentheses, up to a factor of root 2 pi somewhere. So let me call the inner integral something special. I'm going to write f star g at u is the integral from minus infinity to infinity of f of u minus y, g of y dy. So in my notation here, I've really codified the fact that this integral in the parentheses above is a function of u. And as for the y here, you could replace y with any letter you wanted. Z, w, theta. Y is just a dummy variable of integration. And I call this integral the convolution of f and g at the point u. So I start with two functions f and g and a real number u, and then I get this new function, the convolution of f and g at u, by integrating in this way f of u minus y times g of y, integrating with respect to y. And the fact that I've taken f and g in L2 of R by my estimates before guarantee that this improper integral exists. And moreover, I've written now f hat of k times g hat of k is equal to 1 over 2 pi times the integral from minus infinity to infinity f star g at u e to the minus iku du. And that is just f star g hat of k over root 2 pi. So I had to absorb one factor of root 2 pi into the Fourier transform, and I kept the other one out. So what does this say in words? Multiplication on the Fourier side, f hat of k times g hat of k, is the Fourier transform of convolution on the so-called space side, up to a factor of root 2 pi. So if I want to take the product of two Fourier transforms, that's the same as doing the Fourier transform of a convolution. But of course, this doesn't really answer our original question. What is the Fourier transform of the product fg? What is fg hat of k? To answer this question, we're going to assume a lot of things about our functions f and g, and this is pretty elaborate and, forgive me, excessive. I'm going to assume now that f and g are in L1, so they each have Fourier transforms, and they're in L2, so their product is in L1, and they're in C1 piecewise, and they're in fact continuous. So f and g are continuous, and they're differentiable at all but maybe countably many points, and the derivatives are well behaved. And I'm also going to assume that f hat and g hat are in L1, and that these Fourier transforms themselves are piecewise continuously differentiable. This is a lot to assume, I agree. Yeah, yikes indeed. What does this get us? First, we can calculate f of x equals f hat check of x. In other words, because f is in C1 piecewise, and f is continuous, and f is in L1, then f is equal to the inverse Fourier transform of its Fourier transform by our inverse Fourier theory. And we also know that I can switch the hats around and put a minus sign. F check hat of f at x is really f hat hat at minus x. So f is in L1, that means f hat is defined. And I'm assuming that f hat is in L1 too, so f hat hat is also defined. And of course the same holds for g. So if I take my product f of x times g of x, that's really f hat hat of minus x times g hat hat of minus x. Okay? But by my work with convolutions, the product of two Fourier transforms is really the Fourier transform of the convolution. So f hat hat of minus x times g hat hat of minus x is f hat convolved with g hat Fourier transformed at minus x over root 2 pi. Maybe hit pause here for a moment and make sure you feel okay with these three equalities. But in this most recent Fourier transform, I'm evaluating it at minus x, so I can turn a hat into a check and get rid of the minus x. So what do I see? F of x times g of x is f hat convolved with g hat inverse Fourier transformed at x over root 2 pi. And so now if I take the Fourier transform of my original product, fg hat of k, this becomes, okay, we've got a lot of hats here, f hat convolved with g hat, take the inverse Fourier transform on that, apply the Fourier transform back to that, and divide by root 2 pi. And this, in the best of all possible worlds, is f hat convolved with g hat at k over root 2 pi. So now I have an answer. The Fourier transform of fg at k is the Fourier transform of f convolved with the Fourier transform of g at k divided by root 2 pi. So the Fourier transform of the product is the convolution of the Fourier transforms, up to a factor of root 2 pi. And as usual, remember that our conventions for where the 2 pi or the root 2 pi goes may not be the same as some other books or some other papers. So if you're reading somebody else's writing, make sure you know where the 2 pi goes. So why did we need all these hypotheses, these elaborate function spaces for f and g? Remember, to get this to work, we took f and g in L1 and L2 and C1 piecewise and continuous. Remember that a function can be in C1 piecewise and not be continuous, so the last two intersections are actually important. And we also assumed that f hat and g hat were in L1 and they were C1 piecewise too. Why did we need to do this? So if we take f and g in L1 and L2, that tells us that f hat and g hat are in L2 and they are also continuous. This was a theorem from our first week with Fourier transforms. And so that also tells us that f star g is defined. The continuity of f and g allows us to use Fubini's theorem to get f star g both to be defined and in L1 of R. This is a proof that I give in the lecture notes that you can read if you want to, but you may also feel free to skip. And then the continuity of f and of g and the extra assumption that f hat is in L1 or g hat is in L1 gives us the representation f of x equals f hat check of x. Fourier transform theory from last week tells us that f hat is always continuous, so we don't have to do much more work with that. But to get the C1 piecewise, that I think is a bit harder, and we need to assume that. So if f hat is in C1 piecewise, it turns out, from a theorem on convolution that I'm not telling you in this video, that f hat star g hat is also in C1 piecewise and in the continuous functions. And so all this combines with inverse Fourier transform theory to say that f hat star g hat check hat equals f hat star g hat. This was a lot, and I apologize for that, but it's the best way that I could see to get all of our calculations to work out point-wise. I have to be honest with you, I'm not really sure what hypotheses on a function f tell you that its Fourier transform is C1 piecewise. There are some stronger results on differentiating a Fourier transform from last week, but that gives continuous differentiability, not just C1 piecewise. For example, you might say that the integral from minus infinity to infinity of modulus of x times f of x converges. If that holds, then surely f hat is continuously differentiable, but that's kind of a strong assumption. Maybe it's overkill, maybe it's not. So let me apologize sincerely for the mess of all these hypotheses, that we need to invoke all of our inverse Fourier transform theory and all of our existence theory for the convolution. Here's the bottom line. The Fourier transform is easy to define. You just take a function f that's in L1. This is just like how Fourier coefficients for Fourier series are defined whenever your function's integrable on the closed bounded interval. But to go deeper, whether it's with Fourier series or with Fourier transforms, requires rather more technical hypotheses, and this is just a fact of mathematics. But the nice thing is that in the example and important ODE and PDE problems that we'll consider with Fourier transforms, these hypotheses are very naturally satisfied. All the functions that are involved, all the things that are given to you in the problem, they are going to be so nice that all of this convolution theory, all this inverse Fourier transform theory will work out. So rarely will you have to go through this lengthy setup as we did in this video.